Let's find the volumes of some actual shapes, starting with a cone. Okay, so how can we find the volume of a cone? Okay, well, you've got some cone up here, and generally speaking, cones are going to have a particular height and a particular radius. Okay, so to do this using calculus, it's always a good idea to sort of put a coordinate system up. So it makes sense to do one that goes right down the middle as such. Okay, so what do we have here? We've got a radius of r and a height of h. And when we consider the idea, okay, so we're going to sum a bunch of circles. And now let's look at an arbitrary circle. And so if we look at an arbitrary circle, you know, we're somewhere in here, and then we've got to figure out, wait a minute, what's the radius of that arbitrary circle? And we don't quite have it, right? I mean, if we look at it in terms of this value, right? Like what's the radius? It's the x value, right? But we don't know what x is. So what we need here is an algebraic equation. And we can use this straight line where you have 2 points. We've got 0, 0. And we have a second point here. So this is x is r and y is h, r, h. So because we have 2 points, we can actually get the equation of this line. So let's do that first. And we can get different ways to get the equation of a line here. I don't know, like for me, I just automatically think, well, okay, what's the slope? The slope of the line is y minus y, h minus 0 over x minus x. It's actually h over r, okay? And then the intercept would be actually 0, and so the line would be y equals mx plus b, y equals hrx, and that's the equation of the line. You can always get to check these things. Like if you put in 0 for x, you get 0. If you put in r for x, you do in fact get h. Okay, rise over run, h over r. Okay, so how can we use that now to get sort of this, the arbitrary radius? Okay, so first of all, let's think about what we want everything in terms of. Now, if we're stacking a bunch of circles vertically, they're each going to have sort of that dy thickness. Okay, so we actually want things in terms of y. All right, so let's set this up now. What we're trying to do is sum all these circles. We're going from 0 to h. And the areas, let's just write it out. They're a bunch of pi r squareds. And what we've learned is that we want this in terms of dy. Okay, so this particular one, the radius is x, right? The radius is always x, okay? But what we need to do is express x in terms of y. Okay, so it's simple. If we want x as our radius, right, then we need to say what x equals. And so we just cross, you multiply by the reciprocal, and you get r over h times y equals x. Okay, now keep in mind the only real variables here are x and y in terms of the problem. R and h are like, hey, here's a particular cone with a particular r and a particular h. Okay, so what we're going to do then is substitute this in for x, because what we have here, in effect, right, that the radius r is equal to, no matter where your circle is, x. Okay, so let's try that. So we're going from h to 0. We've got the pi, which can go out front, because that's a constant. Now when we square the radius, by the way, these two r's are completely different. I should have named them something different. In fact, why don't I do that to avoid confusion? So if little r is taken, we're just going to call this one big R. So this would be big R squared. It's big R squared. Some people would flip it, but let's just do it like this, dy. Okay, so what is this big R squared? Well, it's x. There, big R. And we just need to substitute in now x, right? Because it's simply the square of x. I'll just write that in another step. So it's going to be x squared dy. See, if it was dx, we could just do that, but we need to put it in terms of y. So now we put the pi out front, and we square this into simply r squared h squared y squared dy. Now, if you know what the formula is of this thing, you might see, because you might wonder, well, okay, if you might know it's 1/3 base times height, 1/3 area of the base times the height. Where does the 1/3 come in? Because you're integrating a square. Okay, now we have everything in terms of y, and we can just integrate. The r squared and the h squared, you're not integrating that, that's just y, so that in effect comes out. So what we get is this is going to equal pi r squared h squared, and then we integrate the y, so we get y cubed over 3 evaluated at h and 0. And so the 0 just goes to 0. When you plug in the h, right, look what happens. You get an h cubed. 2 of the h's cancel out. You go with 1 h in the numerator. So you get h pi r squared over 3, which is the same as 1/3 pi r squared h. Okay, so that is a proof that the volume of a cone is 1/3 pi r squared h using calculus. Okay, fun stuff. Let's go next to a sphere. Okay, how can we get the volume of a sphere? All right, well, I think we can go ahead and set up our x and y coordinate here. And for the volume of a sphere, in effect, we're rotating really a circle, right? You can see how, like, if you rotate this circle around you sort of take your pick. Let's do it on the x-axis, and you kind of end up with a sphere, okay? Now, what this sphere has, it's going to have a radius r, so this is going to be r. And the equation then for the circle would be that x squared plus y squared equals r squared. Okay, and what we want to do to get the volume is sort of sum a bunch of areas. We want to sum a bunch of circles. And so if we look at like an arbitrary cross-section like here, okay, end up with something like this, right? And we want to figure out what's the radius of this thing. And I think what I'll do here, because again, you are working with multiple r's, this one's actually the constant one, and so we'll just call the constant big R squared, big R here. Okay, so what we need to do now is figure out what is the radius of the little circle, right? Because we're summing a bunch of circles. Okay, well here it's clear that r is equal to y, and we have an equation for y underneath. Now, when we're summing all of these, right, these going from left to right, they're each going to have a thickness of dx, okay? So I think based on this information, we are ready to set up the integral, right? So if the volume is equal to, it's the integral from what to what? Okay, so if you want, I mean, there are different ways of doing this. It is symmetric, right? So we could just look at 1/2 of it. And frankly, I think that's what I'm going to do. You could go from negative r to positive r, but you could also double it. You can see it's an even function here, going from simply 0, which makes substitutions nicer, to big R, right? So we're just looking at now the 1/2 of it. We're doing half of a sphere. And our area, right, is what? Okay, let's just write it in. It's A, right, that's what we want to sum. It's a bunch of dx's. Now, it's going to be a bunch of pi r squares, right? So pi, and we just said r is equal to y, okay? And we don't want just y, we want y squared. Okay, we have what y squared is. Y squared is equal to r squared minus x squared, right? And so, r squared equals y squared. And then if you like, y squared equals r squared minus x squared, just putting it up here. Okay, so that's what our little r is. It's pi r squared minus x squared because it's y squared. Right? It's not just y we want. I mean, you could have the square root, but then you square it and it goes away. So that's our a in dx. Okay, and note that like we have everything in terms of x, so this is now good to go. We should be able to do the integral, and the net result, because we have sort of this circle, and you rotate a circle, you get a sphere, should be the volume of the sphere. Let's find out. Okay, so we can pull out the 2 pi. Now we're going to integrate then r squared minus x squared. And so the only variable is x because of the dx. So what do we get? We get r squared, that's just like some constant, so that's just times x, and then that's minus x cubed over 3, right? And then we evaluate that from r to 0. Now the zeros just go out to 0, which is a nice way of just taking half of it and doubling it, and then we just want to plug in r, and so what do we get? So we get this 2 pi, and then I've got r cubed minus r cubed over 3. Okay, well what's r cubed minus r cubed over 3? Okay, this is 3/3 minus 1/3, that is 2/3. So we get 2/3, all right, so it's 2 pi, 2/3 r cubed, and certainly that, and then equals 4/3 pi r cubed, which hopefully you know is the volume of a sphere.